Well, my name is Cristina Marchetti again from Syracuse University, and for the next two lectures, today and tomorrow at 8, I would like to tell you a little bit more about these active systems, but in particular, I will try to tell you about the properties of what we call active liquid crystals. So one of the important differences as compared to the first two lectures is in the first two lectures I gave you examples of systems where that essentially are moving on a substrate in the sense that there is a friction, but there is no real medium. The only effect of the medium, if you like, is incorporated in the models as providing friction. Today and tomorrow, I will actually really talk about active fluids that are composed of active particles, such as bacteria, again, swimming in a fluid, and take into account the flow. That is, for instance, the fact that these swimmers can actually interact, the fluid can mediate hydrodynamic interactions between the swimmers. So we will look at the hydrodynamics of these active liquid crystals and the kind of instabilities and properties that the system exhibits. And today in particular, I will tell you how we can describe theoretically the stresses that swimmers, for instance, introduce in the fluid due to their activity. And how these active stresses can actually lead to various instabilities in the system, and in particular to something that we call spontaneous flow, which is essentially that an active liquid crystal can flow without having any external forces applied to it, only through the action of the internal forces provided by the active swimmers. And tomorrow, I will mostly spend time telling you about topological defects in active liquid crystals. You've heard about topological defects in passive or conventional liquid crystals. And we'll see tomorrow how the topological defects are actually quite different properties in active systems and what their importance is in this case. So just a quick reminder, something I mentioned before. In active systems, we can have, well, like in equilibrium, we can have sort of two types of orientational order in active liquid crystals. Apolar or nematic, and polar, or I would also call it ferromagnetic. An example of a system that exhibits polar order is, for instance, a dense collection of E. coli or bacteria. These are particles that have a head in the tail. We can model them as vectors, but the vectors represent both the orientation of these elongated particles as well as their velocity. And when the system orders in a state with orientational order, this is a polar state. That direction is different from this direction. And it's also a macroscopically moving state. So the order state will be described by a vector order parameter. If this new hat is the instantaneous orientation of one of my swimmers, I can define a vector order parameter as the mean value of the orientation of all the swimmers. And so describe it as a vector. I will call it polarization. I could also clearly is directly proportional to the mean velocity. And the direction of broken symmetry is identified by a unit vector, which is sort of like a polar director. Nematic systems are ones where the units of particles sort of just maybe go back and forth, do not have a head and a tail. And these systems can order in state in nematic order, and the order parameter, therefore, is a tensor, as in conventional equilibrium nematic, so-called the alignment tensor. Now, I will mostly be working in 2 dimensions again, and so let me just, and sometime I will switch a little bit. I mean, Greg Grayson discussed quite a bit nematics, and we discussed them entirely in the term of the director, which is the unit vector that denotes the direction of broken symmetry. I will actually switch a little bit by sometime using just a director, assuming I am deep in the order state, and sometimes using the full Q tensor, which I will need to do when I start talking about defects. So I have the equation written there, but I just want to rewrite it here in a minute. So in general, the full order parameter is a tensor. And if you like, for instance, if this was the z-axis, the zz component of the order parameter will be proportional to the square of the cosine of the angle that these vectors make in the z direction. The cosine itself, the average of the cosine will be 0 because of the head-tail symmetry, so I need to take the square. That's why I need to construct the vector, the tensor. But if I am in 2 dimensions, this is a 2x2 symmetric traceless tensor, right? So in general, in 2 dimensions, the tensor will have 4 components. But it's symmetric and traceless, so actually only 2 of these components are independent. Traceless means that, say, qyy is equal to minus qxx. Qxy and qyx are the same because the system is symmetric. And so I really only have 2 independent components. And I could choose as 2 independent components. Actually, let me write it this way. I could choose a 2 dependent component, say qxx and qxy, or if I write the order parameter in terms of the quantity s that I will call the magnitude of the order parameter and the director, which is a unit vector in 2 dimensions, and therefore the director can also be written, as I done before, as in terms of a single angle theta. I can choose as the 2 independent components the magnitude of the order parameter and the angle theta. And I want to stress this because I will sometimes switch between the 2. So the angle is equivalent to the director in 2 dimensions, and this is the magnitude of the order parameter. What does that mean? It means that the order state, the nematic state, is characterized by having a non-zero value of s, and the disordered or isotropic liquid state as s equal to 0. Okay? Now, so we will construct hydrodynamic equations for this quantity and then add activity. Before we do that, let me actually give you a couple of examples of active liquid crystals. First of all, active particles that actually might form nematic or polar active liquid crystal. This one here is a cell, it's a fibroblast. These are actually experiments that have been done by a French group at Curie, by the group of Pascal Silverzan. And as you can see, this fibroblast just sort of, it's active, it clearly moves, but it kind of moves back and forth. The blue shows the line that it leaves. So it's an active particle, but once you average over fairly short time scales as far as fibroblasts go, it really is not going anywhere. It's just moving back and forth, and many fibroblasts have been shown to order in states with nematic order. An example of a system that orders in states with polar order is our friend E. coli that we talked about before, that clearly has a head and a tail, and moves along directed paths in the plane. And if you have a dense collection of E. coli, they can actually order in states with polar or ferromagnetic order. I will actually mostly be talking about active nematic today and tomorrow, as a matter of fact. And so let me actually show you 2 examples, and I'll probably show more examples tomorrow, 2 examples of active nematics that have been built in the lab. Let's talk about this one first of all, which is simpler. They're both movies. So this is actually E. coli swimming in a nematic liquid crystal. Okay? This is a nematic liquid crystal at equilibrium. No forces are being applied to the outside, from the outside to the system, but the E. coli that is swimming through it is applying forces continuously. And this is actually a chromonic liquid crystal because apparently it's okay for E. coli. E. coli likes it, doesn't die in it. Most liquid crystals are not favorable for bacteria to live in them. And what you can see is sort of self-sustained motion. And if you, I think probably last week you talked about topological defects. You see structures here that have the typical shape of the plus minus 1F disclinations, which are the lowest energy topological defects in nematic liquid crystals. Yes?
So wouldn't this situation be sort of a mix of nematic and polar? Because, so like how do you account for the fact that...
So the reason I say this is a nematic, yes, so if I were to say, I'm going to take a nematic liquid crystal and put in E. coli, what am I getting? In principle, I wouldn't know, okay? But the reason I say this is nematic, and I call it an active nematic, is because the defect structures, which I can see and identify here, and I could do this more precisely by some digital analysis and putting in lines and stuff like that. The defect structures I see here are plus and minus 1F disclinations. And a system with ferromagnetic order cannot have plus, the lowest energy defects are plus 1 defects or minus 1 defects. I cannot have plus and minus 1F disclinations in a system with ferromagnetic order. So actually that's a nice question, it's an important point. The structure of the defects, or the topological defects, is precisely what helps you decide whether the structure may be nematic or polar. Of course, in a nematic I can also have plus 1 defects. They are just higher in energy. Next time you might naturally see them. Okay? Now, the other system I'm going to show here is actually perhaps more convincing as a true nematic, but it's a little bit more complicated. So what I'm going to show you here, so these were actually experiments done by Oleg Lavrentowicz at Kent State. These are experiments done in the group of Zvonimir and Dogic at Brandeis University. And what this is a suspension of microtubule bundles. So microtubules are these polar biofilaments that exist inside cells and form networks inside cells. They are actually quite stiff filaments. They are shown here in green. Kinesin is the motor protein that binds to microtubules and can walk on microtubules. What these experimentalists did is, this slide doesn't show very well, but they build kinesin clusters. They build kinesin clusters by taking streptavidin, which is a drug, and functionalizing kinesin with something called biotin, which binds to streptavidin. So they make cluster by having one streptavidin to which maybe 4, 5, 6 kinesins are bound. So that's your cluster. These clusters can now serve as crosslinks for microtubules. And they also add a depletant that kind of promotes bundle formation. So what you get are bundles of microtubules cross-linked by kinesin clusters. In the presence of ATP, the kinesin walks along the microtubules. The bundles are made by a fairly large number of tens of microtubules, with some of microtubules oriented one way, some of the other. The kinesin always walks towards the direction of the plus end, denoted here by the arrow, actually the other, towards the plus end of the microtubules. And as the kinesin walks, the microtubules are made to move relative to each other, so the whole bundle can sort of, the ingredients of the bundle can move relative to each other, so the bundle can sort of be displaced, it shifts, it reforms, and that dynamics is going to be shown in this movie over here. So the bundle itself is your active particle. You see the bundle that is made to break and reform by the action of the kinesin. The bundle itself is the active particle, and it's an active particle that tends to exert forces on the surrounding fluid that are extensile because they push out. Okay? Now they take a dense suspension of these microtubules in the presence of ATP, and they deposit it at an oil-water interface. And at high enough density, this is the kind of dynamics you get. Sorry you can't see this very well, because it's much better on my, I don't know why. But what you see is a lot of order, orientational order of the microtubules. And again, these dynamics, actually you see plus and minus one of these inclinations being formed, generated, moving around, being annihilated, and so on. And again, no external forces are applied here. So Nematic exhibit this type of self-sustained flows with a constant generation and annihilation of topological details. Okay? And why do people study these things in vitro is because they're trying to understand, if you like, what's the minimal number of ingredients you may need to reproduce things like this, to reproduce this kind of spontaneous motions that we know cells are capable of. Okay, that's the motivation towards behind this. Okay, so how do we go about trying to describe this kind of dynamics? Now, let's go back to something that actually Greg showed yesterday. We are trying to do, I'm going to try to describe this phenomena at the continuum level, writing down some kind of a hydrodynamic theory. Okay? If I were in equilibrium, I would be writing down a free energy for my nematic liquid crystal, which is very much like the free energy that Greg showed you yesterday, only a little simpler in some respects, because I'm in 2 dimensions. In 2 dimensions, there is no twist. So all I have is splay deformation, and here I've written in terms of the director, splay deformation, and band deformation of the order. Furthermore, in most of my talk, I will actually even do something even more drastic. I will actually assume that band and splay are the same, and use what's called the single elastic constant approximation. I will call that elastic constant just K. In general, if I have density variation, I might have also part of the free energy that depends on the density. And if I'm interested in doing sort of what I did yesterday, constructing hydrodynamic equations, my hydrodynamic equations will be equations for the conserved variables, in this case the density and the total momentum, because this is really a fluid. There is no, I will not think about substrate, and so I also have conservation of total momentum. And then I will have the hydrodynamic equations written either in terms of the director and or of my Q tensor. Actually, tomorrow I will probably use the Q tensor. Today I'm mostly just using the director. If I were to have a polar system, I would actually have another term that would be allowed in my free energy, which would be a coupling between band and density fluctuations. But this is only significant if you actually have density fluctuations, otherwise this would be a surface term, and is not allowed in a nematic that must have n minus n symmetry. And since I've been mostly talking about nematic, I really probably won't focus on that. So that would be the free energy. If I were doing equilibrium, I would just work with the free energy, but I'm doing non-equilibrium, so I need to write down hydrodynamic equations. And the way I write, now, liquid crystal hydrodynamics is very complicated, even for equilibrium, okay? So bear with me a minute, this is a little messy. So, but I have 3 equations in principle. Conservation of number of particles, density, continuity equation for the density. Derivative of density is the gradient of the momentum density, which I can also write as rho times flow velocity. Now the Stokes equation, which is simply the statement of conservation of momentum. This is sort of the continuum version of mass time acceleration is equal to force. The force is written as the gradient of something called a stress tensor. The stress tensor is the force per unit area on a fluid element, essentially. And we'll talk about it. We'll talk about it in a minute. And then I will have an equation for the director field. And so far here, I'm actually writing equations that you would have if you were to describe an equilibrium passive nematic liquid crystals. Okay, so the density equation is very simple. The momentum equation needs to tell you what the stress tensor is. In an isotropic fluid, if it wasn't a nematic, the stress tensor will be relatively simple. It contains a pressure, okay? Gradient of pressure gives forces in a fluid. and it contains viscous flows. So what Uij is gradient of velocity. And so here I have shear viscosity times gradient of velocities. These are viscous forces in my fluid. If my system is a liquid crystal, I actually also can generate stresses, so also deformations in the orientational order, deviations from the direct, especially non-homogeneities in the orientational order also give you forces that drive flow. And in fact, one of the characteristics of liquid crystal is a close coupling between flow and orientation. So I have additional terms in the stress tensor that depend on gradients of special inhomogeneity in the flow. This H is something that is known as the molecular field in the nematic liquid crystal. It actually defines the derivative of the free energy, and in the single elastic constant approximation is just the Laplacian of the director. Okay? So basically some complicated terms that depend on gradients of the directors and Laplacian of the directors, and let's not worry precisely about what they are. And then I have the equation for the director, which the director is a vector, so it can be convected by the flow. It couples to omega j is the vorticity, so it couples to the vorticity in the flow. And then again other terms that couple flow and orientation, but also the director can relax with a characteristic relaxation rate gamma. But the main point here is that these equations are complicated, number one. And number two, the important thing to keep in mind is that there is coupling between orientation and flow. Okay? A gradient in the orientation generates flow. A gradient in the flow, vorticity, couples to orientation, generates changes in the orientation, which it's kind of intuitive and not so difficult to see. The coupling involves these blue terms particularly, which have this parameter lambda, and actually I want to give you a feeling for what this lambda does by looking at a very simple geometry. If I were to take these awful-looking equations and write them to describe a simple flow situation, which is a layer of fluid between two planes in sort of a shear flow geometry. So suppose, and again, I'm just talking about passive liquid crystals now, forget the activity. So suppose I have a nematic liquid crystal between two plates. I apply a force to the upper plate, I displace the upper plate so as to generate a flow profile which corresponds to a uniform shear flow, okay, as described by this green arrow. Let me say that and then I ask what happens to the director as described by the angle theta. So I rewrite these complicated equations by assuming that the density is constant, that that's the flow profile that I'm assuming from the outside, that I am in this geometry, which is sort of a one-dimensional geometry where the only thing that variables can depend on is the coordinate across the plane, which I will call y. And I ask, what would be the direction of the director in this system if this was an equilibrium nematic liquid crystal? Well, the answer will be provided by the equation for the director, which I'm now just rewritten in terms of the angle, which becomes much simpler. It's just given by this expression here, where this u is the gradient of the velocity, which is just v divided by the thickness of the sample. So if I'm looking for a steady-state solution, I have a steady-state solution where the angle that the director forms with the x direction is actually determined by this parameter lambda. So what the couplet orientation and flow does, and this parameter lambda do, is that essentially tells you that if you apply a shear flow to a nematic liquid crystal, the director will orient to a specific angle to the flow. And the angle is determined by this parameter lambda. Of course, the angle is given by this value if the magnitude of lambda is bigger than 1. And if the magnitude of lambda is less than 1, clearly this cannot work, and so you get something different. Lambda itself is determined by the amount of order I have in the system and by the shape of the molecules. If you have a rod-like molecule, lambda will be bigger than 1, and on average, the nematic molecule will align with some angle, at some angle with the flow, like indicated here. If your molecules are sort of ellipsoid, fat ellipsoids, actually, then you get a lambda smaller than 1, and then the flow is much more complicated. You actually don't get a steady state. What you get is a complicated state where these molecules tumble in flow. As one says, they keep going like that. So this parameter is important. It tells you about what equilibrium nematics do in the presence of shear and flow. And we will see that it also comes in controlling the behavior of active nematic. And so it's perhaps a bit complicated, but I just thought it would be useful for you to hear about this. So this was all equilibrium nematic. Now what happens when I have activity? What do I need to add to these equations, which are already complicated, to account for activity? For instance, for the fact, perhaps one way to think about it is that I have my passive nematic, and now I put some E. coli in it. How do the E. coli change the equations? So what happens is, actually I want to just focus on this, is that, so I have now, imagine I have swimmers in my nematic. These particles are exerting forces on the surrounding fluid, okay? And because they exert forces on the surrounding fluid, they will generate stresses. And so I will have an additional contribution to the stress tensor, which describes the forces on each fluid element, due to these active particles in the fluid. And actually, let's just look at the next slide. It's really not too difficult to calculate the structure of these active stresses. So what I have here is sort of like a cartoon of, say, one E. coli, or a cartoon of an active particle which is swimming in the fluid. The active particle is generally elongated. It may have a head and a tail, or it may not. This one I've drawn here happens to have a head and a tail. And it exerts forces on the surrounding fluid. But one very important property of these forces is that there is actually no net force. The forces are always in the form of a force dipole. There is no net force exerted on the fluid because, say, there is a thrust force exerted by the particle to swim, but there is an equal and opposite drag exerted by the fluid on the particle. So by Newton's third law, there are no external forces applied to this system. By Newton's third law, the net force on each one, or the net force that the swimmer exerts on the fluid, or the fluid on the swimmer, has to be zero. So in reality, each swimmer exerts a complicated force distribution that I could analyze in terms of force monopoles and dipoles and so on. But there is no monopole. The lowest order term of this distribution is force dipole, as shown here. So I have a bunch of these particles exerting this kind of forces on the fluid. I want to calculate the force density, the force per unit volume or per unit area that they will exert on a fluid element. Well, so that's what I'm writing here. For each one of them, I will call mu hat is a unit vector that tells me about the direction of elongation of this active particle. I have a force minus F applied, using this picture, I have a force that directed opposite to mu hat, that is this force. If that's the position of the center of mass of the particle, this force is applied at center of mass minus mu L. So I put in this delta function here. And then I have a second force directed along mu hat of the same magnitude, which is applied at the center of mass. If I'm interested in continuum, and then I have one of these for each swimmer, so I add up over all of them. If I'm interested in continuum theory, it means I'm interested in deriving a description that will hold on length scales that are much larger than the size of one of the swimmers. So I'm going to expand this delta function, assuming that L is small. And let's look at the blue term for now. To leading order, what I get, clearly the term that has no L vanishes because this two just cancels. And the next term will contain a gradient of the delta function that I can kind of pull out in front. So the next term will have this structure. I think I forgot to rewrite the delta. There should be the delta function of R minus RCM here. And so the next term will be the gradient of something. And the something is what I call the active stress. And if you notice, the something is closely related to the mean value of my tensor Q, which I actually should have written here. My definition of Q, remember, was the average sum of the all particles so J denotes the Cartesian components, alpha denotes the particle, that would be my micro, sorry, I forgot the this is traces. In 2 dimension would be 1F. Or at the continuum level, I could also rewrite these in the following way. Okay? So what I'm getting there for this force, and I have actually forgotten a delta function, so what I'm getting there, I don't know if you can see this unless I turn on the lights. Is that the ith component of the force density that the swimmers exert on the particle is proportional to the derivative with respect to J, and then I have minus FL, and then I'm going to rewrite it because I was a little sloppy there. What I really was getting is the sum of the roll swimmer, mu alpha I, mu alpha J, delta R minus R alpha. Okay? And this, if you like, I can also rewrite as minus some parameter that I will call alpha, or maybe I call it plus. Okay, I incorporated the minus sign in this alpha, so I can write this I as derivative with respect to J of alpha Qij plus 1F delta J. Okay, I didn't write the plus 1F delta J, and I wrote out Q in terms of N. But the important thing here is that this force is the gradient of something. The something is the active stress, and is simply proportional to the alignment tensor or to the product of 2 directors times the magnitude of the order parameter. All the microscopic information about which kind of swimmers I have, how many I have, and so on, are in this parameter alpha. They can actually have 2 signs. It can be positive or negative, depending on what? Depending on whether these dipole forces that the swimmer exerts on the fluid point out or point in. Okay? When the dipole forces point in, alpha comes out to actually be positive. These are called contractile forces, and for instance are the forces you get in an actomyosin network. When the forces point out, as is for instance the case of E. coli, these are called extensile forces, and are the kind of the stresses that you get, for instance, in the presence of E. coli. I actually have a picture here to highlight that. So alpha less than 0 means extensile forces. These particles are also sometimes called pushers. Alpha bigger than 0 are the kind of forces that myosin exert on actin filament inside, say, the cytoskeleton, or are also the kind of forces that some other swimmers, this is the alga chlamydomonas, exert on the surrounding fluids. If you're really talking about swimmers, the sign of alpha also corresponds to whether your swimmer is a swimmer that is propelled from the tail, like E. coli has the tail and swims, or is propelled from the front. So the monas have cilia in their head, they sort of swim like through a breaststroke, and they exert what are called contractile forces of the surrounding fluid. Okay? So there are these active stresses proportional to the order parameter, and the sign of the active stresses depends on the nature of the forces that these active particles exert on the surrounding fluid. And these forces are very, very real. I'm going to show you another image here. So well, first of all, this is the same movie we saw before of these bundles of microtubules and kinesin. And you now should be able to see clearly that these are extensile systems. The bundles kind of fall apart by pushing out, and so they exert extensile, the arrows are out, they exert extensile forces on the surrounding fluid. This other image here is a network of actin and myosin. Myosin clusters, or mini filament as they're called, these blue objects, they exert forces that pull in. These are contractile networks. And in fact, they're so contractile that at high density of myosin and actin, let's have a look at what happens. So this is a network. The red is the actin. And you see what happens. Actually, sorry, I think the red is, no, I think it is the actin. So what happens here is that the myosin is pulling so hard in the contractile nature on these filaments that the actin network is actually broken and collapses in this kind of clumps. Okay, so this is just to highlight the difference between the contractile forces and the extensile forces. Okay? So now, although I haven't really written the equation, so now actually what I like to do is maybe I will write over here the equations in a slightly simplified way that I actually want to use. Okay? So I'm going to make some, and I actually want, now the next thing I want to do is to show you how to use these equations, but first let me kind of summarize them in a slightly simplified way. So I want to write the equations for an active nematic. So to put them together, what I said before. In principle, I would have equations for a density. I would have equations for the momentum density, which can also be written as rho times the flow velocity. And I will have equations, I will just write equations for the director field today. Okay? The equation for the density is simply the continuity equation. But I will actually assume that my fluid is incompressible for now. That means I'm assuming that the density is constant. And if the density is constant, the continuity equation simply becomes the condition that divergence of V is equal to 0. So I have disposed of the density equation. The equation for the momentum, which I will write in terms of rho V, is the Navier-Stokes equation. But it turns out, which is, as I said, sort of a form of continuous version of NA equal to force. Okay? But I will actually look at, I'm actually interested in systems that are in the so-called low Reynolds number limit. Remember, this sigma j, let's write down a simplified version of the sigma j again. Sigma j contains what? Contains the pressure, an isotropic part that describes pressure, contains viscous stresses, which I will write explicitly just to avoid introducing more notation. Shear viscosity times gradients of velocities. Both those terms will be there in isotropic fluid. Contains active stresses, and active stresses are written in the form alpha, Ni, and J, where this N is the director. Okay? And then contains other terms that couple to gradients and Laplacian of the director field, which actually I will not even write over here, because they are higher order term in the gradients. In a regular liquid crystals, these are crucial to couple to the director. But here we have a coupling to the director of much lower order in the gradients. So I will not even, although in many calculations one does take them into account, I will actually not even write these terms here, which are F often of this order. simplify my equation dramatically. In addition, these systems usually are in a regime where, which is called low Reynolds number, which is essentially a limit where the inertia is actually negligible because the viscosity is so large. And so in this low Reynolds number limit, I can actually approximate the Navier-Stokes equation by neglecting inertia and replace it by what is called, so this was the Navier-Stokes equation. I will replace it by what is called the Stokes equation, which is simply force balance, which is simply the statement, the derivative of the stress tensor is here. So far, I've simplified my equations quite a bit. The density equation is this condition. The Navier-Stokes equation has become force balance with the stress tensor given by this simpler form. I still have a fairly complicated equation for the director field, but actually I can simplify that one too if I write it in terms of the angle. And if I write it in terms of the angle, if I'm going to be right, which I might. Okay, that equation will have the following form. The derivative of the angle. I will have, I'm taking a one elastic constant approximation. So K is the elastic constant, gamma is some friction. I will have a term proportional to the Laplacian of the angle. And now is where my trouble comes because I'm not sure about the size. Let me see, I think I wrote it there. Okay. I think I minus, what I have here is gradient. I'm going to write it sort of schematically. These are gradient of velocity. I'm not going to write specifically the components, okay? Because I'm going to specify for particular geometry and then I'll write the components here. I have a 1 minus lambda cos 2 theta here, where lambda is the flow alignment parameter I talked about before. And I will neglect also here higher order terms that couple to higher order gradients of the angle and velocity and so on. So there are other terms here, but I'm not going to try to write it now. So this is sort of a simplified version of my complicated hydrodynamic equations that I would like to work with. And the other thing to keep in mind is the sign of this alpha here. Let's see, we have that. So the extra piece as compared to a passive liquid crystal is this active stress tensor. And the sign of this alpha tells you whether the system is contractile or extensile. That, as we will see, makes a difference. Okay. Now, what I want to do next, I think I would like to. Are there any questions? Yeah, I would like to not to use this right now. But then I want to show you some pictures, I think, at the end. All right. Let's see. Oh no, that's not sufficient. Okay. So what I want to do now is use these equations to solve a specific flow problem, a very, very simple flow problem, in fact, to give you an idea of what exactly stress does. So I'm going to take a simplest flow problem I can think of, which is a nematic film, a film of nematic liquid crystal. Here I have a substrate, a wall. Here I have nematic liquid crystal. Okay. And here is an open surface. The film has a thickness that I will call L. Let me choose some coordinate. This is Y. This is X. I'm going to do this. I have a third direction, but everything is homogeneous in the third direction. I will not worry about this. Effectively, I'm going to solve a one-dimensional problem. I am not applying any forces to this system. I'm I will eventually solve a flow problem, so I will need to know boundary condition. Here I have a free boundary, and here I will impose no slip. No slip means what?
Velocity is 0.
The velocity means that the velocity will be 0 here. Okay. I will also need boundary conditions for the director. I'm going to assume that the director is aligned with each one of the surfaces, that is, that theta is equal to 0 here, and theta is equal to 0 here, because theta is the angle with the x direction. Okay? So I'm assuming anchoring boundary condition. Oh, and free boundary and no forces means that that boundary up there, the stress tensor will have to vanish. Any component of the stress tensor, I just don't do this. Okay? So now, suppose this was an equilibrium liquid crystal, a passive liquid crystal. And I were to solve these complicated hydrodynamic equations. I don't actually need to solve them. What would I find for the velocity? Well, first of all, clearly in this geometry, things can at most depend on the quantity y, right? So I might ask, well, what would be the angle as a function of y? The only velocity component that could possibly be non-zero would be the x component. What would be the velocity as a function of y? And that's all. So if this was a passive liquid crystal, what would I find for this quantity? I have a film of nematic liquid crystal with anchoring boundary conditions. I'm not applying any forces.
Shouldn't theta still be 0?
Well, theta will be 0 everywhere and v will be 0 everywhere, right? It doesn't do anything, it just sits there. Okay. Now let me solve this problem for my active liquid crystal. So let me rewrite these equations now by actually for this specific geometry. So first of all, I'm only interested in one component. I actually have two components with this equation. I have, so things can only depend on y. So I can have derivative of sigma yy equal to 0, and derivative with respect to y of sigma xy equal to 0. That equation actually will determine the pressure, and therefore will determine the mean value of the density, which is whatever it is, I don't really care. Okay? This equation is what I care about. This tells me that sigma xy is a constant throughout this field. On the other hand, I have the boundary condition in the upper plane that tells me that sigma xy at the upper plane has to be 0 because I'm not applying any forces there. So clearly, from these two, I conclude that sigma xy is 0 everywhere. Makes sense? I'm not applying any forces, there are no stresses in this system. I must maintain 0 stress tensor everywhere. Okay, now let's look at the equation for the angle. The equation for the angle, I'll be looking for a steady state, but I can actually, let me just write the time derivative for now. If I specialize into this coordinate system, it becomes k over gamma, second derivative of the angle with respect to y. Now, the only non-zero component of the velocity can be in the x direction, and I can at most have gradients in the y direction. So what I will have here, and I'm not sure about my signs right now, but is dy dx, and then I have a 1 minus lambda cos theta. And actually, and let me also write what the expression for this sigma that has to be 0 everywhere is. The stress tensor, which has to be 0, is given by what? I have eta dy dx, I have shear stresses, and then I have, I think I forgot to write it. Okay, I do need to take into account, I forgot one piece. Oh, no, sorry, here it is. And then I have the active stress. Right, here it is. I have the active stress. It will be alpha, nx, and y, right? But what is nx and y? Nx and y is cos theta sine theta. And so I have plus alpha over 2 sine 2 theta. And I have higher order term that actually I could and possibly should take into account, but I'm not going to write them there. Okay? And again, this has, so let's forget that for now. So this has to be 0. So I have these two equations to solve. If I'm interested in a steady state, this will be 0 as well. Okay. Now you can actually solve these equations analytically. You can actually do the solution with the boundary conditions that are prescribed here. But even without doing that, what you see first of all is that what happens here is that if you didn't have this active stress, well, if the stress tensor is 0, there'll be no flow. Okay. But with this active stress, you can actually maintain 0 stress tensor by having some deformation of the director field, which is balanced by shear stresses. And so what happens in this system, you can show that above some characteristic value of a T, there is a critical alpha. Actually, what happens is that you can kind of combine these two equations and solve them. And what you find is that there is a critical alpha, let's call it alpha C, which is determined by K, by the shear viscosity, by the thickness of the film square, and by this alignment parameter is of that order, up to pi and factors of 2. And for alpha bigger than alpha C, there is a solution. For alpha less than alpha C, your solution is this one, θ equals 0, B equals 0 everywhere. But for alpha bigger than alpha C, there is a solution where there is a spatially inhomogeneous deformation of the director and a non-zero, so there is a θ of y, which is non-zero, and there is a dx of y, which is non-zero. And for this particular geometry, where v has to vanish here and is free up there, your v of y will acquire a profile which is similar, or not identical, to the profile of a shear flow. And the director itself, we do something like that, I don't know, it's totally symmetric. There's some deformation of the director field that you can actually calculate. So an active system shears itself, essentially. That's what you could say here, right? And that's what people have called spontaneous flow. So they talk about the transition from the homogeneous state to this spatially homogeneous state as the spontaneous flow transition. Now, of course, nothing happens spontaneously. The system has an energy input that comes from, say, ATP. It's internal, but it's there. But in a sense, you could say that the system shears itself. Actually, this is something that anybody who knows about liquid crystal knows very well, because this is very much like something called the Friedrichs transition. Friedrichs transition is a transition you can drive in liquid crystals to a state with a spatially homogeneous profile of the director field by applying electric or magnetic fields. Here, it happens spontaneously by driving this parameter that we call activity, this alpha, that essentially tells you how much energy is put in spontaneously into the system by this active particle. So what could the alpha depend on? Well, if you are thinking about the experiments in the microtubule bundles, alpha may depend on the rate of ATP consumption. And it's this alpha that drives the spontaneous flows that we saw before, which clearly are more complicated in structural geometry than these, but ultimately arise from this effect, and this we'll see next time. If you're talking about the E. coli, where the alpha will be proportional to the number of E. coli and to the speed at which E. coli swim, and so on, which ultimately are driven by some nutrient that E. coli consumes. So there is an energy input in the system. But if you just look at the system itself, these flows are maintained spontaneously, and it's now. So the question you could ask then is, does this have anything to do with something that people may actually see in real, say, living cells? These kind of equations have been used to some extent, and I'll tell you more about that tomorrow. They can be used quite well to describe the spontaneous flows I showed you at the beginning of the picture, of the lecture, in vitro systems. But can they actually describe phenomena in living cells? Now, you might have to go back to the more complicated equations and different geometries and so on. And actually, sometimes there are some phenomena seen in living cells that people have been able to describe. I would say almost quantitatively, and I will tell you what I mean by almost quantitatively in a minute, using this kind of equations. For instance, maybe I should, I don't know if I, because I have a picture I was going to show that. Does this come on here? Let's see. Well, I can just tell you a couple of things in words. For instance, cells on subs that are sitting. Yeah, you had a question.
Sorry, I just wanted to ask, your statement that the active system shares itself.
Yes.
Isn't that entirely dependent on the fact that you've chosen one no-slip boundary and the other?
No. If I had chosen, okay, say I have two walls, okay, I will get a different velocity profile, and my parameter for my transition, say if this one contains pi, that one will contain pi over 3. I'm just making this up, okay? The numerical value will be different, but I will still get this. So the boundary condition determine the precise critical value of the offset, and of course determine the type of velocity and the retroprofile you get in your system. But I could have chosen, that the director has to be perpendicular to the boundary, so perpendicular to one boundary aligned with the other. All these different type of boundary conditions will give me this transition just slightly different way.
So in the case of two free boundary, so where you don't have a no-slip, then it would just be a uniform profile? Or?
No, I will get the profile, so if I don't know if I remember that. So in the case of two walls, I get a profile more like a Couette flow. In the case of two free boundary, I actually don't remember, but you do get something there too. Okay, that's. I think you might get something that has a zero velocity in the middle, and the velocity is larger than the walls, something like that. Okay, I don't remember for sure. But all these cases you can get. Yeah.
Your parameter alpha c does not depend on the parameter gamma. Why is it so?
It does, because it does, actually, no, it does. But my parameter alpha c depends on the system size. Okay, so I could also think of these as something that can occur tuning activity, as something that can occur tuning the thickness. And in very, very large system, very little amount of activity is enough to do this. Okay? Although this is true for my system here, which I have assumed, so if it was actually really a liquid crystal film, I said I don't have any friction, so it would be like a freely suspended. Okay? Now if you look at the experiments, the Nematic of the Brandeis lab that I showed you, I said it wasn't an oil-water interface. So actually, in that case, there will be some effective friction, and that will cut off. So actually, we will replace this length scale by the length scale that is defined essentially by the relation of viscosity to friction. So one has to be careful. But the statement that these spontaneous flows occur, it's true in all kinds of geometries and all kinds of boundary conditions and so on. Anyway, thank you. Yeah, I was just a bit sloppy about that. Well, I should end, but let me just tell you that, so people have done, we're using these equations, number of things, but for instance, when a cell like a keratocyte, which is this fan-shaped thing, moves on a substrate, there is this flat region, this fan region, which is called the lamellipodium, is where the actin cytoskeleton is. But the actin cytoskeleton, what really pushes the motion there, are two things, are the polymerization of actin at the front of the lamellipodium, the transport of actin in the direction opposite to the direction of motion of the cell, which is called, I can't remember what it's called, but I write it here. Retrograde flow is called, which is called retrograde flow, and then the repolymerization of actin at the back. So there are sort of two types of motion. There is the actual motion of the cell itself, and there are these flows inside the lamellipodium. So this kind of active hydrodynamic theory can describe quite well the retrograde flows and they've been compared with, they can be imaged in experiment, they can describe quite well the retrograde flows inside the Nematic. Of course, the theory will have a parameter, which is this alpha. Okay? Then people have used the same theory for another experiment. Cells exhibit spontaneous oscillations when they are sitting on a substrate, circle cells. And these spontaneous oscillations have characteristic frequencies, there is characteristic budding at the cell boundaries. Again, use hydrodynamic theory of active gels, as they're called, to describe this phenomena. There'll be a fitting parameter, which is this activity alpha. Use the acting theory to describe waves that will appear in the lamellipodial cells when they are constrained to adhere on the substrate, they're made unable to move, then you see these waves. So there have been a number of experiments that people have been able to fit using this type of theory, and the value for alpha is consistent, essentially. That's why I say almost quantitatively, because of course they all have a fitting parameter, but the value of alpha they've been using in all these different experiments is of the same order. And of course, one is still a long way from describing, the properties of real cells, and I'm sure, and certainly there are plenty of properties of cells that you cannot describe via hydrodynamics, but has been quite a useful and nice approach that people have been now using for some time. Anyway, I will stop here, and then tomorrow I will go back to the Dodging experiments of these spontaneous flows and try to show you how we can actually understand them in terms of dynamics of topological effects in these active systems. Okay? Are there any more questions? If not, I will, let's see. You're going to use the slides, right? You're using slides.